Okay, so it works. So hi guys. So today, well, Ivan's not here and I'm taking over. And instead of combinatorics, I think, or algebra, I forgot. Today I'm going to teach about a little bit of number theory, a little bit of, well, analytic at a number theory, but I mean like of analytic flavor. So let's start with few things. Oh yeah, by the way, I forgot my stylus pen, so my writings might be ugly because I'm using just the fingers. Test, okay. Right, so let's talk about density. So let's say you have a particular property that you're considering, and let's say Fn is the number of positive integers less than or equal to n with that property. With that property. Then sometimes you want to see how dense these kind of numbers with this certain property is in the set of positive integers. Then you might consider this, so Fn over n, right? And maybe you look at this ratio as n goes to infinity. So maybe it doesn't converge, so let's just give it a limit superior. If you don't know what this is, it's fine. Basically, you can just pretend it converges. But limit superior is something like if the sequence is like that, you kind of look at the successive, well, maybe like maximum points, and then you see where it goes, because this sequence will definitely converge. So this is kind of like the density. So as n goes to infinity. So if the density is less than 1, that means if the density is less than 1, that means definitely there are infinitely many bad numbers, right? So infinitely many numbers without that property. So for example, let me see. For example, if we say that Fn is the number of integers less than or equal to n, where it is, let's say 1 mod 10. 1 mod 10. So you kind of expect the density to be 1 over 10. So it's kind of like saying 1/10 of the positive integers have this property in some sense, right? Okay, so there's this theorem called the prime number theorem. Prime number theorem that says that pi n is approximately, well, the same growth order as n over ln n. So pi n is the number of primes less than or equal to n. So it's kind of like our function just now, except the fact that the property now we're talking about is prime. And the prime number theorem says that pi n will grow approximately with this, equal to this function. So this means of the same growth order. That means there are two constants where you can bound pi n by this function here, n over log n over ln n. Okay, so let's see how this can help us in some problems. Okay, so let's look at a problem from Ukraine, I think. So proof there are infinitely many positive integers n such that all prime divisors of n squared plus n plus 1 are less than or equal to square root n. Okay. So I'll give you guys like a minute or two to digest the problem. Maybe just try a little bit of things, and then we can start talking about the method. Well, proof there exists infinitely many such n. Okay, so if you guys are comfortable with the problem, so hopefully at this point you understand what the problem is talking about. So let's begin. And well, there's a square root here, which is quite annoying. So let's, instead of looking at a random positive integer n, let's just replace n with n squared and then prove there are infinitely such n squared instead. So we can literally change this to n to the power of 4 plus n squared plus 1. And then we can change this to n. Right. Well, the thing is, this thing I can factorize, I think, into n squared minus n plus 1, n squared plus n plus 1, right? So here's where it gets interesting. If I replace n with n squared, I can factor this expression into smaller parts. But it doesn't really help much because now we look at each individual factor, which is around the size of n squared, right? Which is around the size of n squared. How do we make sure all the prime divisors are less than n? It's kind of like repeating the problem already because this is also n squared. Okay. So what I'm going to do is I'm going to go one step further and I'll replace n to n to the power of 4. So I'll change the problem into this, n to the 8 plus n to the 4 plus 1. And this become n squared. And if you try to factorize this, you get something very nice. N squared minus n plus 1, n squared plus n plus 1, and this set factor n to the 4 minus n squared plus 1. Right. Okay. So now at least we have only one factor to worry about. So this is the n to the power of 4 term. These two can be easily made to have a prime factor less than n squared. Well, the first one is obvious. So n squared minus n plus 1 is already less than n squared. The second one, well, how can we make sure it has a prime factor less than n squared? So one of the ways I'm going to do it is I'll just make sure this thing is divisible by 3. So I'll just focus. I'll just focus on n equals to 1 mod 3. Okay, so we're kind of restricting our view to a more and more limited set of positive integers. But that doesn't matter as long as we prove there's infinitely many of them. So if we focus on the n equals 1 mod 3 integers, that means these two definitely have a prime factor that's less than n squared, right? The first factor obvious, the second factor because you can divide by 3. And once you divide by 3, that thing is obviously less than n squared. Okay, so that's the first part. Now, if we focus on this, we have to prove that there are infinitely many n where it is 1 mod 3 and n to the 4 minus n squared plus 1 has a prime factor less than or equal to n squared. Okay. So that's the main part of this problem that I'm going to use density to solve. So this is what I'm going to do. Let me scroll down. So I'll rewrite the problem first. So first of all, we want n to be 3k plus 1. Second of all, exists prime p dividing this. Sorry, that does not exist prime dividing this, such that p is more than n squared. The n4 minus n squared plus 1 term might want to change the minus to plus. Is it plus? Oh, if it's plus, okay, sorry, it might be plus. Okay, let me check. N squared. Yeah, I think it's plus. Okay, thank you. So we've transformed this problem into this, and let's hope that there are such n's. So now look at the second condition. There are no prime factors that are larger than n squared, but divide n4 plus n squared plus 1. So I'm going to reverse the question and ask from the point of view of p. Oops. Sorry. Oh gosh. W. Okay. So given a prime p larger than or equal to n squared, how many? Okay, how should I rephrase this problem? Okay, given a prime p, right? How many n satisfy n is less than square root p, and p divides n4 plus n squared plus 1. So now we fix p instead of n. We fix p instead of n, right? We fix p instead of n, and then we ask how many such n fail. Okay, and hopefully we prove that the number of failing n is too small compared to the vastness of the set of positive integers. So if that makes sense. So we focus on this problem. Given the prime p, how many n satisfy this thing, which is to fail, right? To fail. But how many are there? There's an upper bound to how many n satisfies. And this upper bound is just a number. It's not in terms of anything. It's not even in terms of p. It's just a number, like 10 or 20. Why did the n4 minus n squared? Oh, because I think someone corrected me for my factorization. Oh, hang on. Why did my screen go? Okay, here. So, oh, the previous one was correct, is it? Let me check. Just happened. Let me check. N to the 8 plus. Oh yeah, it is minus. Okay, it doesn't matter, it really. Afterwards, they still work the same way. Minus. So instead of fixing n, we now fix p and ask how many n fail. So anyone has an idea how many n satisfies this? So as I said, it's just a number, apparently. It's not in terms of p at all. So focus on this second condition. It's kind of like a mod p statement, right? How many such n's satisfy mod p? Or at most how many? Anyone? Well, let me write it out here. So n to the 4 minus n squared plus 1 is 0 mod p. How many roots are there at most for n? Anyone? Some mod p field or whatever. It's a polynomial of degree 4. So there's at most 4 roots. At most 4 solutions. Mod p. Right? But 4 solutions mod p, and we require that n is less than square root p. So that's like less than square root p means less than p. So there can only be at most 4, right? So the answer is at most 4. The answer is at most 4. Given a prime p, at most 4 n's satisfy this failing condition. Okay. So what does that tell us? Now we can start to bound the density. So, well, let me write this here. So the upper bound of the number of bad. So bad means they satisfy this rate condition, which are numbers that we don't want. So bad n, which are in 1, 4, 7, well, the 1 mod 3 integers, until some large number, let's say 3n minus 2, is basically this. The sum for primes p less than 3n minus less than or equal to 3n minus 2, and then times 4. Because for every prime, there are 4 numbers that, fail for every prime. We want the numbers n such that it fails for all p. So each prime p prohibits 4 numbers in the set of positive integers. Each prime p prohibits 4 numbers, prohibits 4 numbers, prohibits 4 numbers, prohibits 4 numbers. So let's just say all of them are bad. Then those that are not prohibited at all means it does not fail for every single p. So the upper bound for the number of failing n is this thing. Even though there might be overlaps, but the overlap just makes it tighter. So this is the loosest way we can bound it. It doesn't matter if for every prime p that the four numbers prohibited have overlaps or not, because the union is always less than or equal to the sum of individual elements. Okay, so if that makes sense, well, but what is this? This is the number of primes p less than or equal to 3n minus 2 is roughly, it's exactly pi of 3n minus 2. Okay, pi of 3n minus 2. So what's the density? The density is just write density. Density is 4 pi, at most 4 pi, 3n minus 2 over, how many elements are there here that we're talking about? There are 3n, right? Okay, let's just write this in a nicer way. 4 pi 3n over 3n. But you know what the asymptotic behavior of pi is? So that's approximately 4 times 3n over log 3n. Log here means ln, by the way. So maybe I'll just write ln. I'll just write log because that's what most people do anyway for number theory. So over 3n. So this is, well, 1 over log 3n, which obviously is less than 1 when n goes to infinity. So we're done. So there are infinitely many numbers that are not bad. So does that make sense? So what we've done so far is to reduce it to a smaller problem, a problem about prime vectors. And then we look at it from the point of view of primes. For each prime, how many numbers do we want to prohibit? And the answer is at most 4. So every prime prohibits at most 4. Let me draw this out if some of you are still confused. So let's say the prime 2 is a prime. The prime 2 prohibits these 4 numbers, maybe. And the prime 5 prohibits these 4 numbers, and so on and so forth. So what's the density of the union of all prohibited numbers? And apparently it will be less than 1. In fact, it goes to 0, I think, according to this thing. Yeah, it goes to 0. That means there are infinitely many numbers that are not prohibited at all, because we just union the whole thing, the whole prohibited thing. There are infinitely numbers that are not prohibited at all, and those numbers are what we want. Those numbers are what we want. And therefore, we've proven that there are infinitely many n such that this holds. Any questions? So this is also something that might be easily overlooked, which is this thing. If you have a polynomial mod p, there are only at most a degree of f roots, because it's not so trivial, so sometimes we easily forget it. But it's a very powerful thing. Okay, does that make sense? If that makes sense, let's move on to another one. Move on to another one. Let's look at this one. So Q0, Q1, Q2, dot dot dot, is an infinite sequence of integers. Infinite sequence of integers satisfying these two conditions. 1, m minus n divides qm minus qn for all m greater than n. Okay, and second, there exists a polynomial p such that the size of qn is less than pn for all n. So this integer sequence is kind of bounded, polynomial bounded, if you want to use that terminology. Now, prove there exists some polynomial q. Oh, hang on, I didn't say polynomial here. Polynomial. There exists some polynomial q such that qn equals large qn for all n. So in fact, all of the terms in this sequence are images of some fixed polynomial. So again, I'll give you guys a few minutes to digest this problem, kind of get a feel of it, and afterwards we can well, talk about it. So I want to talk about it after every one of you are comfortable with what this problem means. So any questions about the problem? Okay, if not, let's begin. So we want to construct this polynomial Q, right? And it satisfies for all positive integers n. So that means if I take enough terms, the first few, let's say n terms, if I take n to be enough, sufficiently large, and I take the Lagrange interpolation of that polynomial, we should get Q, right? I mean, in some way, and we have to prove it as well. So what we're going to do is let Q be such that Qi equals Qi for I equals 0 to D. So D we don't know. We don't know. We just let this be D and then see whether we can talk about D afterwards. Okay. So now, what can we do? We can have, let's say, Qn. Remember Qn, remember the first condition, right? Well, I can say that n minus, should I write this? For any I between 0 and D, n minus I divides Qn minus Qi. So that's the condition 1. But this is Qn minus big Qi. Okay, so is that fine? So Qn is congruent to big Qi mod n minus I. Can we write this in a nicer way? And yes, we can. Because Qi is congruent to Qn mod n minus I. Well, look at the left hand side and right hand side. They are completely independent of I. So it's a really nice thing. And it works for I equals 0, 1, 2, 3 until D. So that means, well, it must be the same. They are congruent mod the LCM of n minus 1 dot 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 n minus D. Okay. And this is a really large number if we choose our n carefully. Or I mean, when n is really large, it's a very large number. And when that happens, we can kind of expect Qn. I mean, we can kind of expect these two to be forced to become the exact same integer when the mod is really, really large. So let's do that. So let's bound this thing. Let's bound this thing. In fact, lemma, the LCM of n minus 1 dot 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 n minus D is kind of the same growth order as n to the D plus 1. Well, why? If you just simply multiply all of them together, it's quite obvious that would be n to the D plus 1. But we want to look at the LCM. So what's a nice way of doing that? So lemma is that this thing is this. Well, we can prove it by, okay, fine. Let's just see anyone has any ideas on how to prove this. So we can prove it's easily less than or equal to, because it must be at most the product of all of them, which is n to the d plus 1 with the same growth order. How do you prove the other side? How do you prove it's at least some constant times n to the d plus 1? Primes larger than or equal to d plus 1 cannot be a factor of 2. Factor of primes terms. Wait, what? What do you mean? Cannot be a factor. Okay, as in p divides. Oh, okay. Okay, two terms. Okay, that makes sense. Yeah, so if you look at prime factors, well, primes that are larger than d can only divide at most one number inside here. So n to n, well, n minus 1 until n minus d, these d numbers, d plus 1 numbers, they are almost co-prime in that sense, except for a few primes, right? For a few primes. And how do we handle that remaining primes that are less than d? In fact, I think I should do this on Microsoft Notepad, right? uh, yeah, after this question, I'll just switch to Microsoft Notepad. I don't want to draw anymore. Well, you can kind of like divide some common factors if you want to take the LCM. If that kind of makes sense. Let me see. So let's come down here. The LCM of, let's say, A, B, C, D, I think it should be more than or equal to A, B, C, D divided by the pairwise GCD of every single term. Well, GCD AB, GCD AC, blah blah blah. So there are like n-2 terms. Well, mainly just purely because, well, roughly speaking, the factors here, they kind of cancel all of the extra primes, if that makes sense. We can probably make this more rigorous, so let's do that. It's kind of like the version of the two variable case. The LCM of A and B is AB over GCD AB, right? It's just that here we are kind of deleting even more common factors. So maybe let's say A1, A2, dot, AN. So can we prove that? So let's say A1 is P1 to some power A11, P2 to some power A12, P3 to some power A13, dot, dot. And A2 is P1 to 21, P2 power 22, P3 power 23, dot, dot, dot. And so on. So the LCM, L, is just P1 to the maximum of A1, well, AI1. I don't really know a nice way of writing this. AI1, I, yeah. And then P2, the maximum of AI2. And why is this more than or equal to alternate S, alternate X? Why is that more than or equal to the right hand side? So in other words, we can just focus on the factors of P1. In other words, this thing says Y is maximum of AI1. If you look at the VP, is greater than or equal to A11 plus A21 plus dot 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 plus A plus whatever actually, plus let's say AM1 minus the pairwise GCD. So how many pairwise GCDs are there? What happens when you take pairwise GCD? You get like the minimum, right? Like AI1, AJ1. In fact, this is easy. Every single term, which is not the maximum term in this list, will eventually get cancelled off, right? If you arrange A11, A21, A31, blah blah, A1, AM1 in increasing order, every single term that isn't the greatest one is the minimum of some pair, and it will be destroyed by this subtracting sum. I hope that makes sense. So in fact, you're subtracting a lot of terms, a lot of terms. Right? So this identity is true. And we can use this and prove that lemma that we have just now. So why is it this order? Because this thing is greater than or equal to n minus 1, blah, 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 n minus d over the pairwise GCD. How many pairwise GCDs are there? There are kind of d plus 1 choose 2 of them, right? D plus 1 choose 2 of them. That number. But every single pairwise GCD is at most d, right? Euclidean algorithm. N and n minus d, GCD at most d. So this is at most d to the power of d plus 1 choose 2. D plus 1 choose 2. But d is a constant. D is a constant, and we're looking at varying n. So this thing, of course, this is n to the d plus 1. So it is growing very, very large, growing in this order. Okay, if that's okay, let's continue. So why does this prove the problem? If Qn is congruent to large Qn mod a very large number, that means really hard to move around. So for all n, this is true. Mod some kind of number which is of order n to the d plus 1. But remember, these guys are, at bounded, well, they are bounded by a polynomial. They are bounded by a polynomial. So let's see. If Qn is not congruent to Qn. Sorry, what I'm saying. If Qn is not equal to capital Qn, then Qn minus Qn, absolute value, will be at least this term, which is of order d plus 1. So now, how can we choose d appropriately? What kind of d can we use? Well, remember p, right? Remember p. So this is more than or equal to Qn plus Qn. So Qn is more than or equal to this plus this. But Qn is a polynomial of degree d. So this is actually also n d plus 1. So this doesn't work because this, remember, this thing is less than or equal to Pn. So we just choose d to be the degree of p. Choose d to be the degree of p. Then this thing will be broken for large n. And that would mean Qn is equal to Qn for sufficiently large n. For sufficiently large n. And that actually kind of proves it already. For the remaining finally many values of n, you can just use condition 1 and bash it out. Really. Like if you're not convinced, I can just write it out for you. It's just like this. For the remaining n, Qn mod n minus m is equal to, or for the remaining m, I think, is equals to Qm. Hang on, what am I writing? Sorry, no, this is Qn, this is Qn, congruent to Qm for large m. So you increase n to infinity, then you can prove that Qm is equal to Qm. So we're done. Yeah, I think I should really change to Notepad now. It's really hard to draw with a finger. Okay, any questions? Any questions for this problem? So I'll just repeat the proof. I'll just repeat the proof, a very summarized version of the whole proof. So I let large Q to be the Lagrange interpolation obtained from the first D terms, 0 to D. In fact, later we will say D is chosen to be the degree of P. Then you would get that Qn is congruent to the polynomial n, mod a very large number. This number is growing at the rate of n to the d plus 1. Okay, n to the d plus 1. So that means you are forcing these two integers to be equal by choosing d to be the degree of p. Otherwise, the differences will be too large and you will violate the second condition. So that means that Qn must be equal to large Qn for sufficiently large n. So at some point onwards, this is true for all n. But then for the remaining finally many numbers, you can just prove it very easily like that. Okay, let me change to Notepad so I can type faster. I believe I was talking really, really slowly just now. Notepad. Okay, stop the share and share screen. Okay, so for the next part, first I'll introduce this lemma because we're going to use it later more often. The sum of the sum of reciprocal of primes squared, so basically sum of p of 1 over p squared, is less than 1/2. So very simple statement. Can anyone just prove it to me very quickly? The sum of reciprocals of prime squared is less than 1/2. Or anyone has any idea how to prove this? Then we can skip a lot of steps. Yeah, exactly. So I think you can just use, so you know that the sum of 1 over n squared is, I should probably write brackets, it's pi squared over 6, right? The Basel formula. So that means the sum of odd 1 over n squared plus the sum of even 1 over n squared is pi squared over 6. The sum of odd 1 over n squared plus, if you even, I can factor a 1/4 out, sum of 1 over n squared equals pi squared over 6. So sum of odd 1 over n squared plus 1/4 of pi squared over 6 is pi squared over 6. And you just use pi squared over 6. I think that bound would be, I think that bound needs to be more tightened. Pi squared over 6 is more than, maybe it works, maybe, I don't know. But let's just use this. This is the tighter bound. The sum of odd 1 over n squared would be 3/4 of pi squared over 6. That would be pi squared over 8. Okay, so that's around, that's less than 3.2 squared over 8. What's that? 0.01 times A2 squared 1024 10 to the power of 2 to the power of 10 over 2 to the 7. 2 to the power of 7 is 128. So 1.28. About 1.28. And you want to reduce it to 0.5. So 1.28 minus 1 over 1 squared minus 1 over, well, remember to add back the 1 over 2 squared because that's prime as well. Minus 1 over 9 squared. Sorry, no. Yeah. 2, 3, 5, 7, 9. Minus. Is that? Yeah, I think that's enough already. This is 1.28 minus 1 plus 0.25. Ah, that's slightly more. That's slightly more than 0.5. I think we can improve on this 1.28 here. 3.15 maybe. Let me see if that improves the bound. 3.15 squared divided by 8. Yeah, it's 1.24 apparently. Yeah, then it works. 1.2403. And this is 0.4903. So that's less than 1/2. Yes. So the sum of reciprocals of prime squared is less than 1/2. We're going to use that later. Okay. So let's do this one. So A1, so problem, A1, A2, ... is the sequence of all square-free positive integers in ascending order. In ascending order. Prove that there are infinitely many n such that an plus 1 minus an is 2020. So square free means it doesn't have a, well, it's just a product of distinct primes. That means square free. Okay. So what can we do as a first step? We don't want to jump to the conclusion straight away. We're going to start by giving some conditions first. So what we want is positive integers n such that n and n plus 2020. So n and n plus 2020 are square free, while everything in between are not. Okay. So we can use CRT to kind of make sure this happens. So use CRT to find n is congruent to A mod B, so that n plus 1, n plus 2, ... n plus 2019 are all not square free. Okay, that should be easy. But of course, we'll come back and say, and we'll come back and control what B is afterwards. In fact, I'll just write it down here. Why not? So this is where, how should I write this? So this is by choosing primes P1, P2, ... P2019, such that n plus 1 is 0 mod p1 squared. N plus 2, or I'll just write it like that, pi squared, n plus I. So this ensures that they're not square free. So now we have these numbers such that n and n plus 1 until n plus 219 are not square free. So now the extra condition we need is that n and n plus 2020 are square free. So extra condition we want n and n plus 2020 are square free. So again, we are going to do some density bounding. So for a fixed prime Q, right? What's the density of numbers n is A mod B, where Q squared divides n. Where Q squared divides n. And another question is for a fixed prime P, Q, what's the density of numbers n congruent to A mod B, where Q squared divides n plus 2020. Then afterwards, we will add these two densities together and prove that they are less than 1. So let's answer the first question first. So the first question is, n is A mod B and n is 0 mod Q squared. Okay. So, well, there are two possibilities here, right? Either Q and B, either Q is a factor of B or Q is not a factor of B. So either n is 0 or n is some number C mod B squared Q, BQ squared, or n is still this thing, right? Or this. And we'll just choose, actually, we can choose our PIs such that this never holds, right? So what does that mean? That means, how should I write this? And what we want this case actually. We want this case. We don't want this case. This case is quite rare actually. And the way we delete this case is by going back a step and choosing our PIs carefully. I think yeah, exactly. So n plus I is 0 mod pi squared. And n is 0 mod q squared. If these two have overlaps, that means I is 0 mod q squared. If q is some pi. But this, okay, maybe like that. When q is some pi, which is the case where this latter occurrence happens. So this is when q is some pi. When q is some pi, we get that I is a multiple of pi. But this cannot be true when pi are more than 2020. So we go back to there and we just let pi to be primes that are more than 2020. Therefore, n is C mod B Q squared. So the density is 1 over BQ squared. Okay. Well, same thing for this one. It's the same answer. You just choose your PIs carefully in the end. Again, I think it's the same condition. So density for this one is also 1 over BQ squared. Right? So now, the density of numbers that fail both conditions, that fail either condition, is at most this thing, 1 over BQ squared plus 1 over BQ squared, because there are two cases there, over 1 over B, because we're looking at a case where n is some fixed mod B, some fixed number mod B. And we're going to sum it up with all primes Q. But this thing is less than 1 by the lemma just now. So we are done. So we first control the numbers from n plus 1 to n plus 2019. We first control those. Those are easy to control via CRT. Okay. Now we want to control n plus 2020. We want them to not be square free. We want them to be square free. So what we do is we fix a prime Q and we see what happens, or how likely does it happen for Q squared to divide some number n in this list, n equals a mod b. And apparently the density would be 1 over BQ if you choose the PIs correctly. But we just have to make sure they are more than 2020. So the density is 1 over BQ squared. And same thing for this condition is also 1 over BQ squared. So the density of numbers that fail either one of them, you just add them up, divide by 1 over B, use that condition of the reciprocals of primes lemma. It's less than 1/2. So this is less than 1. So that means there are numbers that are not prohibited by any Q. And that means those numbers are square free. Right? Is it too hard or something? So it's like we use the primes to destroy as many positive integers as we can. And we prove that the density of the numbers destroyed is less than 1. So there are infinitely many more numbers that are not destroyed, basically. Why does the density of Q squared dividing n equals to the failed ones? Shouldn't... Oh, okay. So why does density of Q squared dividing n equals to the failed ones? Shouldn't Q squared divide n? Hang on. The density of numbers. Give me a second. Q squared dividing n. Then I subtract. Wait, no, square free means... Yeah. Square free means you don't let it happen, right? You don't let this happen. we want n and n plus 202 to be square free. Square free means no squared primes divided. So that's why I look at what cases are there when there is a prime squared dividing it, and we add the densities. So these are the ones we don't want. Yeah, I kind of got confused what square free means just now. I thought it's also there's a square inside. Okay. In fact, should we continue doing density or something else? If I just give a few practice problems, and I shall turn over to another topic. So this one is also quite fun. Prove that, prove that there is a constant C greater than 0 with the following property. If A, B, and N are positive integers such that the GCD of A plus I and B plus J is more than 1 for all ij in 1, 2, 3, ... n. Then min AB is at least Cn to the power of n over 2. So I'll give a few hints here. So first of all is to you look at the grid, you look at the matrix, construct a grid where the ijth entry is GCD A plus I, B plus J. Okay. So, and then use density to prove that there are at least n squared over 2 cells that contain prime factors greater than n. Greater than n. Okay, this has something to do with the 1 over prime squared sum again. So use density to prove that this thing holds. Basically, you want to look at the primes that are less than n, and you prohibit as many as possible. Apparently, you cannot prohibit all of them. You can only prohibit at most half. So the remaining at least half contains large primes. So that means n squared over 2 cells have large primes. Since there are n rows and n columns by pigeonhole principle, some column or row has, well, contains at least n over 2 cells that contain prime factors greater than n. So GCD A plus I and then B plus J contains a large prime factor which is greater than n for n over 2 values of J. Well, that basically means that A plus I itself contains a large prime factor other than n. In fact, contains n over 2 large prime factors greater than n. Then we're basically done actually. So that A plus I is larger than n to the power of n over 2. Of course, we have to make sure these primes are all distinct, which is easy to prove. These primes are all distinct. So similarly, b plus j is more than n over 2. Basically, that's how you solve this. Well, these are just hints. You can, so I'm not going to spoil too much as well. You can try it yourself. Okay. If that's fine, let's just talk about something else. Let's talk about something else. Let's talk about multiplicative functions. So does anyone remember what multiplicative functions are for number theory? Anyone remembers what this is? Well, they are functions that satisfy this relation. So f takes inputs from the positive integers to anything, to any complex number actually, such that fmn is equal to fm times fn for coprime mn. So whenever you have two coprime factors to split, you can just split the whole function completely. So any examples of multiplicative functions? Any examples? Mobius function. Yeah. Oh yeah. D is one of them. Yes. So sum of divisors. Sum of divisors dn. Hang on. No, there's number of divisors. Sorry. Number of divisors dn. Sum of divisors is also a multiplicative function. So the easy one, yeah, also phi. So phi n. You probably know what that is already, so I'm not going to write it here. Let's look at the obvious ones. So the obvious ones. So the identity function. ID. So IDN is just n. So that's an obvious one. And there's also one more, which is this. The one function or the unit function. So E. So E1 equals 1, but E anything larger than 2 is 0. Oh, sorry, larger than 1 is 0. Okay. These two will be actually quite important afterwards when we talk about convolution, because they kind of act as like the identity element in some group. Okay. So first of all, a property of multiplicative functions. What can you say? So this is an obvious theorem or obvious proposition. A multiplicative function is completely specified by values at prime powers, right? So assign numbers to prime powers, then that means you have successfully constructed a multiplicative function, because that will determine the image of every single element in a set of positive integers. So that's obvious. Okay. So I'm going to introduce a new function, multiplicative function, called the Mobius function. It's normally denoted by mu, but should I go to Google and copy a mu symbol here? I think I should. Mu symbol. Oh yeah, thank you. So laggy here. So mu n. So I define it this way, right? Mu 1 is 1. Mu prime is -1. And mu prime powers is 0 for all k greater than 1. So can anyone write out the complete form of mu? So for an arbitrary integer n. For an arbitrary integer n. So when is mu 0 at? Where does mu vanish? Sorry, I should write p is prime. So for example, what's mu 2? Mu 2 is -1 because 2 is a prime. But what's mu 4? Mu 2. Okay, mu 1 is 1. Mu 2 is 2. Sorry, -1. Mu 3 is -1. Mu 4 is 0 because it's p squared. Well, mu 5 is -1. Mu 6 is mu 2 times mu 3, which is 1. And so on, and so on. So the most general form is that mu n is 0 if n, sorry, maybe I should write, is -1 to the k if n equals p1, p2, blah, 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 pk is square free. And mu n equals 0 otherwise. Okay. Well, it's a very weird function, but apparently it will be quite important because it allows us to do a lot of things. So the first theorem is this. The sum where d runs over all of the divisors of n of mu n, of mu d is equals to en. It's equals to en. So i.e. if n is 1, the left hand side is 1. If I is not 1, the left hand side is 0. I mean, let's prove this directly. So obvious when m equals 1. Assume n is larger than 1. So say it has prime factors p1, p2, blah, blah, pk. Okay. Then, well, what really contributes a non-zero contribution to the left-hand side? All of those factors that are not square free, that have at least 2 repeated prime factors, they all cause the Mobius function to vanish. So the left-hand side, the sum of this mu d is actually just the sum of let's say this set is P. Sorry, let's say this set is S. Then the sum of all subsets of T, and then -1 to the size of T, right? So every square free prime factor is just some kind of subset of this, the product of some subset of S. Does that make sense? And for each subset T, the product of the functions under the Mobius function, the product of the elements under the Mobius function is just -1 to the power of how many prime factors, which is the size of T. So it's just this one. Well, this is just the sum from k equals, I equals to 0 to k of -1 to the k to the I, and then k choose I, which is 0, right? By the binomial theorem. So you can write this 1 - 1 to the power of k, which is 0. Okay. Oh no. What's about to follow? I have to write a lot of sum notations, and there will be some notation subscript, a very long thing, and it will look very ugly in Notepad. Okay, I think I have to switch back to whiteboard. Okay. Okay. So just now we've proven this thing. So the sum of divisors of n mu d is equals to En, the unit function n. Okay, now how do we, for example, calculate, let's say, phi n? Can we write this in terms of a nice thing? So this is how we're going to do it. Phi n, I can write it like this. So how should I write it again? M is less than n. GCD of Mn is 0. 1, sorry. And then 1, right? Okay. Then notice that this is just this function, right? E to the GCD, well, E of GCD Mn. E of GCD Mn. So we can write this as, by the previous theorem, D divides Mn of mu d. So let's just probably underline what's the variable that we're focusing on. So this is M, this one is M, this one is M, this one is D. Right? So N is fixed, but M is not. Now I'm going to swap summations. I'm going to swap summations. So what should I let D be? Like, where should it run over? What should it run over? So D must satisfy D divides the GCD of Mn, and D is also less than or equal to N. So I can just use this condition first. D divides N. And then we look at the condition for M. What should N run over? So M should be, so look at these two propositions. When does these two propositions hold true? So it's when M is a multiple of D and when M is less than or equal to N. Okay, so M is a multiple of D. So I should write it like that. Like this. So these are all the conditions for M. And then mu D. Okay. But what is this exactly? What is this exactly? This is just M equals D, 2D, 3D, 4D, 5D, blah, 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 until N. Right? D, 2D, 3D, 4D, blah, 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 until N. So this is literally just D over N. N over D, mu D. N over D mu D. Okay. Is that clear? So if that's clear, let's just write this in a nicer way. I will define this thing. So given two functions f and g, I define f star g. So this is called the conjugation of fg of n to be the sum of this f n over d g d. So the above theorems here, so this thing says that phi is equal to the identity function star mu, right? Okay. In fact, we're going to look at this conjugation operation a lot more times if we actually have time. Right. So where should I go from? Let me see. Yes, a few properties. Just a few properties first. So conjugation is commutative, for example. And conjugation is also associative. So F star G star H. So that allows us to do like operations using convolution as well. And you can probably find a lot of things. So for example, D is the number of divisors function is 1 star 1. Okay, 1 is the function that gives 1 for every single n. Okay. And sigma, the sum of divisors function is ID star 1. Right? So think about y. Plug it into the convolution definition. So just now we've proven that mu star 1 is E. The first theorem that we've proven just now. The first theorem just now. And then here we've proven that phi equals ID star mu. We can go further. In fact, we can try to take any two nice functions, conjugate them. it probably is something nice. Mu star 1 is ID. Okay. So let's just see if we can solve a problem using convolution. Let me see if I've taught enough things that allow us to solve this problem. So what I want to do is I want to add up all of the numbers that are less than or equal to n, coprime to n. So what's the sum of numbers of positive integers less than or equal to n, coprime to n, coprime to n. Oh wait, I think the answer is obvious without convolution. Okay, never mind. Let's just try it anyway. Anyone? Well, you can use the pairing trick, which is kind of the easiest trick, the easiest way to do this. So if D is coprime to n, then n minus D is also coprime to n. And you add them up, it's like n. Since there are phi n of them, the answer should be equals to n over 2 phi n, right? N over 2 phi n. But we can also do it via convolution if you want. So if you want to use convolution, basically it's this. So this is equal to this, the sum of all numbers less than or equal to n, GCD less than, GCD mn equals to 1 of m, right? So I'm going to write this like this times m times the Mobius function. Sorry, like this identity. And then I'm going to swap summations. So swapping summation is a very nice trick. I mean, for this question, it's probably pointless, but I just want to show. Sometimes you want to swap summations. So to swap summations, first of all, what's D running over? So D runs over the factors of n. And then what's M? M runs over what? The multiples of D but then it should be less than that or equal to n. M mu d. So now we can sum this up first. Right, we can sum this up first, which is easy to sum. So this is just literally d plus 2d plus blah plus n times mu d, which is equal to, what's this? This is d times n over, sorry, what am I doing? N times n over d plus 1 over 2 times mu d. Okay. Yes. So expand this all out. This is n over 2, the convolution of id and mu, n, plus n over 2, the convolution of 1 and mu. So you know that this is n over 2 phi n plus n over 2 e n. So it's either n over 2 phi n, or when n equals 1, that would be 1 over 2 plus 1, so 1. So if n is 1, if n is larger than 1. Okay. Okay. What other problems are there? Let's try and see if we can do something. Okay. Yeah, this one is nice. So just now I said convolution acts like a group, right? So the thing is, for any function, if I convolute, if I apply convolution with e, I get back the function, right? Very obvious. If you plug it into the thing. So E kind of acts like the identity element in a group. E kind of acts like an identity element of the group. So we can define f minus 1 such that f convolution f minus 1 equals to E. In fact, that can be done. Can be done if and only if f1 is not 0. So I'll leave that to you as an exercise. I'll leave that to you as an exercise. So if f1 is not 0, you can find such an inverse for convolution. And another nice thing about convolution is this. If f and g are multiplicative, well, just now I didn't mention anything about multiplicative functions. But if f and g are multiplicative, then f star g is also multiplicative. Also multiplicative. So that means if you have like an identity such as mu squared, let's say this thing, mu squared d over phi d, right? Mu squared d over phi d. Let's say how we want to simplify this. If it's multiplicative, we can just focus on the prime powers. Remember that. If it's a multiplicative function, we can just focus on the prime powers. So this one here is, hang on, f star 1g. Yeah, exactly. So this is multiplicative ish. This is mu squared over phi star 1, right? And since this is multiplicative, we know that this whole thing is multiplicative. And therefore, we look at cases where n is a prime power. And you should get something nice. So d divides prime power, mu squared d over phi d. Well, what is this? This is, notice this thing vanishes for all prime powers with exponent larger than 1. So this is just mu squared 1 over phi 1 plus what? Plus mu squared p over phi p, which is 1 over 1 plus 1 over p minus 1. And this is p over p minus 1. Therefore, if I define this to be Fn, then f to the pk is equals to p over p minus 1. Can we think of a function that obviously satisfies this? Like a multiplicative function that obviously satisfies this. Okay, it might not be that obvious, but if I write it like that, you can probably see it. So what is it? It's the identity on the top and the phi function at the bottom, right? Identity on the top, phi function on the bottom. So that easily tells us that Fn, since f is multiplicative anyway, we can extend this for all n. So Fn, which is what we want to find just now, mu squared d over phi d. We can say this is equal to n over phi n. So that's a property of multiplicative functions. You just have to look at prime powers. But of course, I haven't proved to you that the conjugation of two multiplicative functions is a multiplicative function. So you have to really, we don't have time for that, but you can try to prove it. Right, okay. So So I'll just leave an exercise. So 1 over phi n equals the sum of d dividing n. 1 over d f d n over d. So find f. Let me see if it's multiplicative or not. Okay, so it's just n to anything. So you want this thing. So find f. So there's a quick way, there's a long way. So the quick way is using convolution, but the long way you just do it by bashing. Okay. Any questions? So what I'm doing here is basically like an introduction to analytic number theory, actually. So you probably start by learning some properties of convolution, multiplicative functions, and yeah, these kind of things. So any other questions before we end the class? Okay. If not, then I guess we can end the class here. So, okay, now just stop the video. And I guess good luck for your test tomorrow. Can I send this whiteboard? Sure. Okay, then if nothing else, then I'll say goodbye. See you next time.